Hey guys, hopefully this video works for you guys, and that way if you need to look over it again, you can, and brush up on a few things. I want to go through 8.104 in your code book, the maximum circuit loading. If you guys could turn to that as we end up going through it. A lot of this stuff is kind of confusing when you end up going through it for the first time. Even I have to read through it a couple times just to make sure I'm 100% on what I'm talking about. But let's go through this bit by bit, and we will make some sense of it. So 8.104 maximum circuit loading, I'm just going to read off the sub rule, and then I'm just going to put some explanation to it and give you an example of what it means, and then we'll go on. And then I want to finish with a little bit of stuff on transformers, just a basic step up, step down calculations. So shouldn't be too bad of a class. All right. So sub rule 1, the ampere rating of a consumer service feeder branch circuit shall be the ampere rating of the overcurrent device protecting the circuit, or the ampacity of the conductors, whichever is less. So it's saying your service feeder branch circuit shall be the rating of your breaker, your overcurrent device, or whatever is calculated. So if I had a service, and let's say it was 100 amp service, my breaker is rated at 100 amps, but then the ampacity of my conductors are rated at 125 amps, or sized at 125 amps. Well, I can't very well just go, so this is my conductors, this is my breaker. I can't go ahead and say, oh, that 125 amp conductor, yeah, my circuit's good for 125 amps, because it is limited by that 100 amp breaker. You know, sometimes when you end up running wire, the wire could be upsized simply due to a voltage drop calculation, or maybe you upsized it just because you had extra of those conductors. Just because the conductors are rated for that amount doesn't mean that the whole circuit is rated for that amount. So I'm limited by what the breaker size is, so for the overcurrent device. So my consumer service feeder or my branch circuit is now determined by the smaller of the two. You know, and let's say potentially I had conductors that were rated at, let's say, 80 amps instead. If they were rated at 80 amps, well, now that is what my circuit's rated at. It's rated at the lesser of the two. It'd be rated at the 80 amps. So no longer is it rated at the 100 amp breaker size, but instead it's rated at the 80 amp size. So that's number one, and that's just a quick little example of that. It wouldn't be that far off. It'd probably be more like 95 amps is what we'd be looking at, the difference between the two, but that is what is rated. It's the lesser of the two, whether it's the rating of the wire or rating of the breaker. Okay, so let's go on to number 2, and I lost my whiteboard eraser, so I'm just using a little piece of paper towel here. All right, so number 2, the calculated load in a circuit shall not exceed the ampere rating of the circuit. So let's say I calculated out what my circuit load needed to be, and let's say I realized that I needed 115 amps. Okay, so all this is saying is that, okay, well, my ampere rating that I'm requiring for my load, or my calculated load is 115 amps, I can't then go and put a 100 amp breaker in. I can't put a smaller breaker in place of, or to supply the load of 115 amps. So obviously if I had that, my draw is gonna be significantly more than what my 100 amps breaker is gonna be. So I'm gonna end up finding that I'm gonna have nuisance tripping all the time, right? So I always have to make sure that my breaker is larger, or at least adequately enough to cover what the calculated load is of that circuit. And I'm gonna try to take a few more notes as I'm verbally just talking about it. If you can just write down a few little blurbs as you end up going through. Okay, now we're gonna go on to 3, sub-rule 3. Sub-rule 3 says, the calculated load in a consumer's service, feeder, or branch circuit should be considered a continuous load unless it can be shown that in normal operation it will not persist for. So I always have to assume 100%, unless in these two cases that a total, so this is part A, a total of more than, or it will not consist for a total of more than 1 hour in a 2-hour period when it does not exceed 225 amps. So not more than 1 hour in a 2-hour period for less than 225 amps. And then the second thing is for B, so it's A, and then B, not more than 3 hours in a 6-hour period for more than 225 amps. And this should be for less than or equal to 225 amps. And then if it runs for more than 3 hours in a 6-hour period, for more than 225 amps, then, so if it does not operate for more than 3 hours in a 6-hour period for more than 225 amps, it's not considered a continuous load. So hopefully that makes sense, and they're just looking at their, in the term, and you'll hear it more in advanced, you've probably heard a little bit, but it's duty cycle. How often is it going to operate? So the main idea with this is that if that circuit is not going to be operating, basically it works out to less than 50% of the time during a set period or a set window, then it can be classed as a non-continuous load rather than a full continuous load. This stuff can get tricky as you end up going through code dealing with continuous and non-continuous, and yes, some of the wording does get a little confusing with that. So hopefully that there ends up helping out a little bit. Dropping everything here. All right. So now we're going to go on to 4. Okay, so number 4. Number 4 says a load of a cyclic or intermittent nature shall be classified as continuous unless it meets the requirements of sub-rule 3. So this basically says, so like a cyclic, so it turns on and off in a set period of time, or if it's intermittent, comes on spontaneously. Um, so that would be like heating loads, so electric heat, or for like a baseboard heater or a boiler, something along those lines. And it's saying with this that yes, it has a duty cycle, but you can't assume it's not a continuous load unless you can prove sub rule 3 that it doesn't operate for more than an hour in a 2 hour period for less than 225 amps, or more, not more than 3 hours in a 6 hour period for over 225 amps. So as long as you can make sure that that is the case, then it can be classed as a non-continuous load. But if not, so let's say, let's write something at least. Heating loads, intermittently turning on unless can prove meets requirements of sub rule 3, needs to be viewed as continuous load. Okay? Alright. Hopefully you got that down. You can pause that if you didn't have time to write it down in its entirety. Now the last two sections of 104 can be a little troublesome as you're looking through them. So let's do 5, sub-rule 5. So sub-rule 5 says, where a fused switch or circuit breaker is marked for continuous operation at 100% of the ampere rating of its overcurrent device. So that is basically saying, let's say I have a 3-pole 15 amp breaker. It's saying that it can be used at continuous operation at 100% of its ampere rating. So that would mean like a typical breaker would trip at 80%. So 80% of 15 would be 12 amps, so that's typically what we'd end up seeing. There are some cases where there are breakers that can run at 100% of their rating. So this breaker would run at 15 amps in one trip. They're extremely expensive, but sometimes in certain applications you need a breaker that runs at full capacity, continuous duty. In maybe certain hazardous locations you may require that. So we have a breaker that's running at continuous operation at 100% at the ampere rating of the device. So 15 amp rating, runs at 15 amps. It's classed for continuous duty. Typically they're continuous duty at 80%, which is in the next portion. It says continuous load as determined from the calculated load shall not exceed the continuous operation marking on the fuse switch or circuit breaker. So the continuous load calculated is just saying for the second part shall not exceed the continuous rating. So this falls into what was talked about at the start in the first couple sub-rule 1 and sub-rule 2, is that I can't have a calculated load of 16 amps and be put on that breaker. So that part's easy enough to understand. So the continuous load as determined from the calculated load shall not exceed the continuous operation marking on the fuse switch or circuit breaker. And, so this is A, except as required by item B, which we will get into in a sec, shall not exceed 100% of the allowable ampacity of conductors selected in accordance with sub-rule 4. So sub-rule, or sorry, not sub-rule, but section 4. So what they're determining there, and because it says allowable ampacity of conductors, there's multiple, those would be multiple conductors. So it's referring to wire that's been sized based on table 2 and 4. And so it says, except as required by item B, shall not exceed 100% of the allowable ampacity of conductors selected in accordance. So the continuous load as determined from the calculated load. So our calculated load cannot exceed the breaker size and shall not exceed 100%. So when we go to calculate out the breaker size and the wire size, neither the breaker size nor the wire size shall exceed the set breaker size. So I can go up to 100%. So if my wire is rated for 15 amps as the maximum draw on it, I could put in a wire that was rated at 15 amps. But what I couldn't do is maybe that wire is only rated, and I'm going to do it based off the 15 amps. Maybe that wire is only rated for 14 amps. Obviously that wouldn't be a case. But let's say it was rated at 14 amps. I couldn't put in a 15 amp breaker because now I've exceeded the allowable ampacity of that wire. Because if that breaker can operate at 100%, I could see 15 amps going through that wire. And obviously if I'm exceeding the current draw on that wire, then that wire is going to overheat and begin to mount. So realistically, if I had said maybe a 30 amp breaker to start, a 30 amp breaker, and I've sized my breaker. So I've calculated a 30 amp load. I've put a 30 amp breaker in. I couldn't put a wire rated for 25 amps on that breaker because now I'm exceeding the rating of that breaker. And with everything you're looking at when you're sizing things, is you always want to protect that wire. You never want that wire to overheat. So the size of the wire chosen and the size of the breaker chosen are always picked to at least supply to the load what's needed to be run, but then you never want to exceed the size of what your breaker can handle, and you never want to exceed the amount of current that wire can actually handle, because then that's when fires end up starting. But with option A, it's based on table 2 and 4 because it's conductors, or in cables. So there's multiple wires in that. So that's what it refers to. So this whole rule basically states that whatever my calculated load is, the overcurrent device or breaker maybe the other, where a fused switch or circuit breaker is marked for 100%, it's more saying it the other way around. I'll do it as per how it's stated so it doesn't get confusing. Alright, so where breaker or overcurrent device is rated at 100%. The calculated, so the circuit load can't exceed breaker size, and the breaker size, you can see down that little breaker size can't exceed 100% of wire rating. Okay, so just write that blurb down. So breaker size can't exceed 100% of wire rating. So you're fully protected with that. All right. So now we're going to look at what it means when it's talking about option B. And this ties close to everything else. So option B says shall not exceed 85% of the allowable ampacity of single conductors selected in accordance with subrule 4. So this is referring to single conductors, and single conductors would be those that would be in free air. And so that would be tables 1 and 3, so it's referring to tables 1 and 3. So the continuous load as determined from the calculated load shall not exceed the continuous operation marking on the fuse switch or circuit breaker, and shall not exceed 85% of the allowable ampacity of single conductors. So that's just saying if I have a wire that's rated at 100 amps, it just means that I can't exceed an 85 amp breaker. And what ends up being found with this is, and the reason why you can't exceed that, so typically in free air, if you have two conductors that are the exact same size, the conductor in free air, because there's air around it, is able to dissipate more heat in the air. When you end up sizing it, based off this rule, I can actually get away with a smaller conductor to feed this. So because the conductor's smaller, they don't want the breaker to exceed 85%, because now that smaller wire can't dissipate heat as well as a larger wire would be. So it's not looking at the same size wire, we're now looking at a wire that it may have been a number 10 in a cable, but now as a single conductor in free air, it may only be a number 12 or a number 14. So because it's only a number 12 or a number 14, potentially, it can't dissipate heat because there's resistance as well in the wire. So that's all that is saying. So between A and B, we're looking for between A is multi-conductors from table 2 and 4, and B is single conductors from tables 1 and 3. So that breaker can be at 100% operation and be on a wire that's rated at 100%, but that breaker size can't exceed it when it's tables 2 and 4, and when it's tables 1 and 3, that breaker can't, it can be at 100% operation, but it can't exceed 85% of that that wire size. So if I selected a wire and I wanted to put it in and the breaker size exceeded 85%, I would just have to go to a larger wire in that case. Okay, so that is 5 done. And now we're going to move on to 6. So 6 says, where a fuse switch, and this is very similar to the one before it, where a fuse switch or circuit breaker is marked for continuous operation at 80% of the ampere rating of its overcurrent device. So this is basically every situation that you would see day to day, where a fuse switch or circuit breaker is marked for continuous operation at 80%. So that would be, we've got a 15 amp breaker. It's rated at 80% of its operation at continuous duty, which would be 12 amps. So the first instance is an instance where we would barely ever see, where we see a fuse or breaker rated for 100% of its rating. And here is the most common, where that breaker or fuse is rated for 80%. So operation at 80% of the ampere rating of its overcurrent device. The continuous load as determined from the calculated load shall not exceed the continuous operation marking on the fuse switch. So that's just saying if, and what you end up seeing every day is if I calculate out my load and my load is 14 amps, well 14 amps is greater than 12 amps. So I need to go to the next larger size breaker in that case. So my calculated load cannot exceed 80%. And then it also says, and except as required by item B, shall not exceed 80% of the allowable ampacity of conductors selected in accordance with section 4. So because it says conductors, it's talking about tables 2 and 4. So this is in A, that my I had a brain fart for a second. And except as that shall not exceed 80% of the allowable ampacity of conductors. Yeah, so my breaker the continuous load, I was right the first time. Continuous load cannot exceed 80% of wire size. So let's say my wire size is going to give me availability of 25 amps. And from that, I end up going to size my wire, and my wire size is, let's say, gives me a maximum of 30 amps. So this is for wire size. Wire size is 30 amps. What's 80% of 30? 80% of 30 is 24 amps. Well, my continuous load says I need to be able to have a wire size that is at least 25 amps. Well, the 24 amps over here has been exceeded on that breaker, so, or the 24 amps is not enough. So in section B, this is what we would use every day when we go and calculate out, okay, I have a load that is, let's say, 16 amps. Well, if my load is 16 amps, if I multiply that by 1.25, it means I need to put at least a 20 amp breaker on that. If I size and get a 20 amp breaker, which is 80%, or 1.25 times or 125% larger than 16, then I also need a breaker that is suitable to carry that load, which is also 1.25 times greater. So a breaker size, and looking now from the other way, if a breaker is sized at for continuous duty at 80%, I'm looking at my breaker size, it's 80%, so it's let's say a 50 amp breaker at 80% is 40, so that just means that my continuous load calculated can't be larger than the 40 amps, and also my wire size that I put in, that wire size has to be large enough that the calculated load doesn't also exceed 80% of that value. So two very close rules between the two. One just has a breaker at 100%, and then this one's looking at 80%. The last part of the rule, if we go down to B, so B states, so let's go back up. So the continuous load as determined from the calculated load shall not exceed the continuous operation marking on the fuse switch or circuit breaker, and shall not exceed 70% of the allowable ampacity of single conductors selected in accordance with section 4. So it's talking about single conductors, which is in free air. So this one's just saying that my continuous load, again, can't exceed 80% of fuse or breaker. And then if my wire is size from tables 1 and 3, so table 1 and 3, which is in free air, that the calculated load cannot exceed 70% of wire size. So in this case now, I have a breaker that is maybe a 100 amp breaker, and my calculated load is 80 amps, so that works. But in this case, I wouldn't be able to use a wire that's rated at 100 amps because 70% of 100 is only 70, so I then have to upsize my wire to possibly one that's rated for, what's an easy one? Let's just say it's rated at 120, yeah, so 120 amps at 0.7, that should be 84 amps. So if I had a wire that was rated for 120 amps, 70% is 84. Well, now if my demand, so I need 80 amps, or that's my calculated load. I put my calculated load on a 100 amp breaker, that's within the 80%. And then I need a wire that in free air is at least sized to 70% of that wire size. Well, 70%, I've got a wire that's good for 120 amps, 70% is 84 amps. Now that calculated load is within that 84 amps, and that's where that rule comes from. So hopefully that made sense going through that, and I didn't confuse you anymore. And then yeah, if you need to go over this a few times, you're more than welcome to. Okay, so now I'm going to go through some transformer calculations. I don't want to give you any more headache with the code stuff. So this is just gonna be very simple, very basic, some turns ratio stuff. If I have an incoming voltage, and these are like the transformers that are sitting on the desk in B1032. If I've got 120 volts coming in and 24 volts on my secondary, so this is my primary, and this is my secondary. If you divide 24 into 120, you get 5. So 120 is 5 times larger than 24, so that means that I have a 5 to 1 turns ratio. So this would be a step down transformer. Anytime you have a higher voltage going to lower voltage, it's a step down transformer. If it started as 24 volts and went up to 120 volts, then that would mean that it is a step up transformer. There are times as well where you see, let's say 208 volt to 208 volt. This would be an isolation transformer. So my turns ratio is 1 to 1, so I have no gain in voltage or loss in voltage. And isolation transformers are typically used in instances where you want to protect something. So because I don't have a electrical connection from one side to the other, and it's just a magnetic connection because of those coils inside, I can have maybe an instance where I have an audio booth. And in my audio booth, I have a lot of very sensitive electronics. Well, if I come into an isolation transformer and put that between my main conductors and my audio equipment, then if there's any power surges in the building, or maybe lightning hits the building and is going along the conductors, I don't have a direct electronic connection between that side and the audio equipment, and it ends up being connected because that surge isn't going to pass through that isolation transformer. Okay, so that's the reason why those would be there. So step up, step down, and then isolation are the 3 most common types of transformers. There's always also current transformers and stuff like that, but we're not going to get into that. So we have a step down transformer in this case. All that means in the grand scheme of things is that I have more turns, so 5 times more turns on one side of the transformer than I have on the other side of the transformer. So I could potentially have, I could have possibly, let's say 600 turns on one side and 120 turns on the other side. They're likely going to be a lot more, but it refers to the number of turns or windings inside that transformer. So it could even be possibly 6,000 turns to 1,200 turns inside. So in this case, if we do the most basic, I would know then that for every turn of that coil inside that transformer, there would be 24 volts per turn. So 24, 48, and 72, and so on and so forth, 96, 124. And then if I had 2 turns on the secondary, if I have 24 volts per turn, if I had 2 turns on this side instead of 1, I would end up having 48 volts instead of the 24. Interesting things with this is transformers always come with a KVA rating on them, or your volts times your amps. So let's say that I had a KVA rating of, or VA rating. Let's just do, let's do 12 volt amps, or that would be 1.2 kVA. If I had 1200 volt amps on rating on my transformer at 120 volts on my primary, what would that mean for the amount of current that's being supplied or could be used by that transformer? Well, if I take my VA, that's power, right, divided by volts, that's going to give me an ampacity of 10 amps. So I have 10 amps on my primary. From the primary to the secondary of the transformer, my kVA is going to be the same. My losses are going to be negligible through my transformer. So if my power on the primary side is 1200 volt amps, then my power on my output is also going to be 1200 volt amps. So input and output power are the same. But what I've found is that my voltage has now went up on the one side, and my voltage has went down on the secondary side. Well, if the voltage is up on one side and then ends up going down, but my power remains the same, that means that something else has to go up. And the only other thing that can go up in this case is that of my current. So I have to maintain the same amount. So if I do 1200 volt amps divided by 24 volts, that gives me a current of 500 amps. So also notice that my current here, or sorry, not 500, 50. Notice that my current here also has the same ratio. It's also a 5-to-1 ratio, but it's in the opposite. So my voltage has went down by 1/5, but if my voltage goes down by 1/5, then my current is going to go up by 5 times. It's the opposite. Okay, so it's kind of like a teeter-totter from one side to the other side of that transformer. So let me just put a couple of examples up here. Let's do 600 volts and 100 volts. So this is my primary, secondary. And I want to figure out what my turns ratio is. I want to figure out, and let's do 6 kVA. So I want to know what my turns ratio is, and then also what my current is. And then also in these questions, I might make a little handout for you guys, but you can also do them where I have a variable that's missing. I may not have on one side, so I could say it's a 600 volt. Actually, I might do a little bit. So yeah, so let's do this. So 600 volts on the primary, 100 volts on the secondary. I want to know turns ratio and current. And then now I'm going to have another one. It's going to be 10 kVA transformer. We're going to have 200 volts on the secondary. And we're going to have let's do a 20-to-1 step down transformer. So I need to know the primary side, and I need to know what my current is. Okay, so let's start with the first one, if you wanna pause and work through it, that would be awesome, to see if you can figure out what that is. And we are going to do, so turns ratio, always divide the smaller into the larger. So we have 600 volts divided by 100 volts. That gives me an answer of 6. So this is 6 times larger than that one. So we have a ratio of 6 to 1. Now we're looking at what our current is. So we can either take both of them and divide our currents out. But we can also use our turns ratio as we were doing before. So our voltage is going to be 6 times smaller, but our current is going to be now 6 times larger on this side. So we only need to calculate out one of them if we want. So let's do the primary. Primary is 6,000, or sorry, the secondary rather is 6,000 volt amps divided by 100. So we have 60 amps. Okay, so we have 60 amps on this side. So that means that our voltage is 6 times smaller from primary to secondary, but then if we went primary to secondary, it means our current is now 6 times larger. So whatever this value is, this side should be now 6 times smaller. So if we do 60 divided by 6, divided by 6 is equal to 10. That means that this side should be 10 amps. And if I take 6,000 volt amps divided by 600, it will give me an answer of 10 amps. All right, now let's go on to the next one. So we need to figure out what our primary is. And we've got a turns ratio of 20 to 1. So that means that this side is going to be 20 times larger than that side. So 200 times 20 is 4,000. So we have 4,000 volts. On this side, it's a 10 kVA transformer. So let's see if we can figure out the current. So 10,000 divided by 4,000. I believe that should be 2.5. Yep, 2.5. So that means our current is 2.5 amps on this side. And it should be 20 times larger on the other. So 2.5 times 20 is 50 amps. And if you take 10,000 divided by 200, you should get 50 amps. So that should be a good start. Next class I have you, lab class on the Monday for some, and then for the others I have tomorrow. I'm gonna go through, actually that'll be a week later for the group tomorrow. So next week's classes I'll have a bunch of questions for you guys, transformer questions, turns ratio stuff that you can go through. Okay, so hopefully that works for you guys, and look forward to seeing you guys again. Okay, bye.